We'll begin our first session on matching. To start off the session, we have Professor Meghna Nasre from IIT Madras. What better way to start the session than an alumni of IISc? She completed her MTech at IIT Bombay and PhD at IISc, and she was briefly at UT Austin and has been at IIT Madras since 2013. Please welcome Professor Nasre.
Yeah, thanks. Okay, so first of all, I would like to thank all the organizers for inviting me to this great workshop on Winter School on TCS. And as Tasi said, yeah, it is a pleasure and a privilege to be here at IISc, your alma mater. Lot of memories and lot of nostalgia. So thanks once again to the organizers. So without further ado, I'll just get started. So we are going to talk about matchings in these two sessions. And all the things that I define will be I'll talk about will be completely defined. So at any point, if you find that something is not clear, feel free to raise your hand and ask. It's just because I am not explaining it well. Okay, so before getting into the actual material, I'll just technical part of it. We'll start with a small motivation for the problem. So I guess most of you have gone through this joint seat allocation or counseling. So I guess most of you have done that. So just show of hands. The JOSA allocation, right? So all of you know that. So the JOSA allocation has these students on one side, and there are programs on the other side. So what is this not visible?
No. It's darker
very thin.
Would be better. It's slightly thin.
Okay.
Is it okay? Yeah.
This is light.
Someone from the back confirm. Yeah. It's glaring and.
Can you read?
Are you able to read? Is it right? Is it okay? Okay.
You can try the red
Readable,
one.
no problem.
Sure. Thank you, Siddharth. Okay, I'll try using this. So there are these students on one side. There are these programs on the other side. By a program, I mean we have, let's say, computer science at IIT Madras, mechanical at IIT Bombay, and so on. And students are interested in getting assigned to these programs. Programs, on the other hand, are interested in getting good students. So we have to find a matching or an assignment, and that is the essential problem. But what is the difficulty? The students have what are called as rankings of programs, and programs rank students based on certain rankings. And what are these rankings? How do they rank it? the JEE mains or the JEE advanced. The NITs use the JEE mains, the IITs use the JEE advanced, and so there are these two rankings that are used. But the crucial point is there is no consistent ranking of all the students. For example, you cannot draw one ranking of all the students and say that just consider the students in this order and allot them their choices, right? So that is something that cannot be done, that because different programs rank students in different orders. In particular, in this example, two rankings are used. Students, of course, have their individual preferences, and they are given by the students themselves, so they need not be consistent. But yet, and given the scale of the problem, that is, we have about a few lakhs of students who are participating in this, and several of these programs that are institutes that are participating, yet over the years there is no merit violation. There has been no court case. So how do these people achieve this, where there are no merit violations and there is no violation of rank order? This is achieved because there is something which is used, which is a algorithm
Increase the font size a bit. From
Okay, sure, I will do that. So we use an algorithm, or it uses an algorithm with theoretical guarantees. And this is where theory comes into play so much, that this is a problem which is of so much practical importance, and yet there is something underlying which is very, very theoretical, which makes sure that over the years we ensure that there are no rank violations or merit violations. So what we are going to see in today's first lecture and the second lecture is what is this algorithm with theoretical guarantees. But before we get into that, we have to define our problem very carefully, and we cannot deal with such a complex problem which is the joint seat allocation. So we are going to look at a slightly textbookish version of it, but you will get all what is there for understanding why this student to program allocation in joint seat allocation works, even though we are going to look at a slightly textbookish variant of the problem, right? So, and there is where these matchings will come in, but I'll define them slowly as we go along. Okay. So what we will have are two sets which we will call as A's and B's, and in your mind you can keep, so is this part okay to write, or should I write on this?
No, you can.
Okay, I think these people can't see. Okay, sure. So on this side it is clear. Okay, so what we will have is, we'll have two sets, the set A and the set B. In your mind you can think of the set A representing students, the set B representing programs, and we have some student, the agents, we call them agents or students, A1, A2, A3 up to N1, and there are programs which are B1, B2 up to Bn2. So these two sets may not have equal number of members. We have these A's and B's. As we said, the students give preferences over programs. Similarly, the A's give preferences over B's. So let's say that A1 finds B1, B2, B3, B1, B3 and let's say some B7 acceptable. Then this student or this vertex, I'll just call it vertex after this, gives a rank order of these acceptable partners. So whenever I draw this edge, I'll say that A1 finds B1 acceptable. In turn, B1 also finds A1 acceptable. We'll assume this whenever I draw this edge. So I believe everybody is familiar with graphs. Okay, so I'll assume that. Okay, so we'll say that A1 submits a preference list, and the preference list is B1, B3, B7. This can also be conveniently represented by putting ranks on these edges, saying that A1 ranks B1 as the top choice, B3 as the second choice, and B7 as the third choice. And this is what is a ranking that every A can submit. In turn, a B can also submit its own ranking, For example, B2 can rank. Okay, so I did not draw this edge, so I should not draw it now. So B2 can rank its acceptable partners in its own way. So B2 ranks, let's say A4, A3, A4, AN1 in its order. Maybe A4 is its top choice, A3 is its second choice, and AN1 is its third choice. And this can be the submitted ranking. Although in this example it so happens that both of the vertices have 3 edges incident on it, that may not be the case. It can have as many edges as it likes, and it need not rank everybody. Right? So this is the input to our problem. So the input to our problem is in fact a bipartite graph where there are 2 sets A and B. The edge set represents that you have mutual acceptability. That is, if there is an edge between AI and BJ, then AI is acceptable to BJ and BJ also is acceptable to AI. And then there is a rank ordering. So every edge has 2 numbers which represent the rank. The lower the number, the better the order. Is this okay? Yeah. And what is our goal? So we are given this graph G, which is A union BE. Our goal is to compute an assignment M, which is a subset of E, and we'll call it a matching. And I said we will restrict our problem. So instead of saying that students can be assigned to programs where in the real world setting every student is interested in getting assigned to at most one program. In fact, every student wants to get assigned to one program, but some students may be left unassigned. Every program typically has a capacity saying that the program can accept 50 students, 75 students and so on. In our setting, we'll restrict it to saying that every program has a capacity of 1. Right? So we will call such assignments a matching. That is, it is a subset of the edge set, and I'll always denote a matching by writing these edges or having a wiggly thing on the edge set. But a matching is not only a subset of the edge set, such that no 2 edges in M share an endpoint. Right? So for example, once I have assigned A3 to B2, I cannot take AN1 and assign it to B2. This won't be a valid matching. So this is forbidden because I said that no 2 edges share an endpoint. Similarly, if A3 does not rank B7, there is no way that I should assign A3 to B7. So I can only have a subset of the original edge set. Therefore, I cannot take A3 and assign it to B7. Right? So these are the rules of the game. So we have an input graph, which is a bipartite graph. Each edge is ranked, and this sometimes we will write it as this preference list, which is written in this way. But this can be translated into ranks which are given on the edges. Every edge has 2 ranks, one from the A side A endpoint, the other from the B endpoint, which says how well this vertex is rated with respect to the endpoint, right? So this is the input. And our goal is to come up with an assignment. But it's not only good to say that we will come up with any assignment. We want something which are good assignments. So let's wait for a minute and ask what do we mean by good, or what does good mean to you?
You have to define some metric over which we can decide on the compare to basically matchings.
Good. Okay. So if I give you some matching M and somebody else comes up with N, I would like to know whether I choose M over N. That is your way of defining it. Yeah. So you can possibly take the edges and look and assign.
Some all the weights maybe.
Some all the weights. Okay.
So if the sum is lower, that means maybe my matching is better.
Okay. Yeah. Good. Any other suggestions?
We can have like maximum assignment can also be metric.
Okay.
We want
So,
maximum A to be assigned.
Okay,
Maximum
good.
B to be assigned.
okay. So maximum size. Is that what you mean?
Yes.
Okay, maximum size. Then there is some metric in terms of sum of, I would just say sum of ranks, that's what I believe you mean. And lower the better. Right, so it is interesting. Any other suggestions from anybody? Oh, yes.
For a some other AI that has a lower rank than that A should not have a institute that is more preferable to the A.
Okay. Okay. So possibly I'll try to encode this. So maybe we'll take a concrete example and look at it. So. Yeah, so this is our concrete instance that we have written. So it has 3 vertices in the A side, 3 vertices on the B side, and let us come up with some candidate assignment. So I assign A1 to B1, I assign A3 to B2, and I also assign, so this is rank 3, although I did not write it, yeah, and I assign A2 to B3. So it's clear from this example that this certainly satisfies this max size, because this is the largest that we can come up with. So it is the maximum size assignment in this example. Now let us ask whether this assignment is good. One can check what happens with respect to the sum of the ranks, and also whether there is a better assignment with respect to the sum of the ranks. I believe that you are going to sum up ranks on both the endpoints of the edge, right? But I'll leave it to you to check out what happens. But let's look at everybody and let's ask whether the A's and the B's are happy or are they dissatisfied. So A1 has certainly no reason to crib because it is assigned to the best partner. Similarly, B1 is also having no issues because it is assigned to the best partner. Remember that every B can accommodate only one vertex, therefore that is the only thing that it can accommodate. A2 is unhappy. A2 would have liked to get assigned to B1. So A2 is unhappy. Similarly, if A2 doesn't get B1, it would have liked to get assigned to B2. It doesn't get that also. So A2 really seems unhappy. So let's similarly, if you look at A3, A3 is happy because it gets his top choice. If we look at the vertex A2, a natural thing to do for A2 would be whoever has given this assignment, disregard this assignment or disregard this entire process and just go and individually approach that program or whoever is the coordinator of that program and say that I am interested in applying to your program, please give me admission or please accept me. When it approaches B1, B1 says that I would have liked to give you, but sorry, I have only one seat and I rank A1 better than you, therefore I cannot accommodate your request. So therefore A2 gets turned down from B1. But when A2 does the same thing, so A2 says, okay, sorry, it's disappointed and it doesn't get B1. A2 goes and applies to B2. It sees that B2 has one seat, but it has accommodated a student or an agent which is lower preferred than A2 with respect to B2's own ranking, which seems to be a bad thing to do. And therefore, this pair which is there, which is A2, B2, is a problematic pair. We don't call A1, B1 a problematic pair because while A1 wants to improve, A2, B1 is a problematic pair because while A2 wants to improve, B1 is not willing to accommodate it because B1 has already accepted a better preferred agent. However, we call A2, B2 a problematic pair or what we will call as an unstable pair. And an unstable pair, to even define an unstable pair, we require a candidate assignment. So we were given this input instance, we were also given a candidate assignment which is given by these red wiggly edges, and then we looked at this pair A2 B2 and we said that it is an unstable pair or a problematic pair if the following two conditions happen. That is, we call a pair AB unstable with respect to a matching M if, first of all, AB should belong to E. That is, it should be an acceptable pair. That is, it should be an edge in the graph. It should not be a matched pair because it is not something that is already assigned. We are not asking whether A2 B3 is an problematic pair. So it belongs to the edge set. It does not belong to the matching. And A prefers B over its partner. So when I say partner, it means the assigned partner in the matching M. And B also prefers A over its partner in M. If both these conditions are true, which happen to be true with respect to A2, B2 in this example and with respect to this assignment, then we say that such a pair is unstable, right? So is the definition of an unstable pair clear, or are there any questions? Okay, so I repeat, we have an instance, we have a matching M which is given to us. The matching must satisfy these properties. We will call it an unstable pair if it is an edge in the graph, it does not belong to the matching, that it is not a wiggly edge, and both the endpoints prefer each other to their current partners in M. Of course, we'll also say that a vertex prefers being matched to remaining unmatched. So if a vertex is unmatched, it always prefers any edge over being left unassigned. Now, I mean, it's clear that maximum size assignments need not have this property of not having unstable pairs. Right? This example already shows that. So, but if you see that why these unstable pairs are problematic, because an unstable pair is really a merit violation or a rank violation, and we would like to avoid that. So we would like an assignment, or we will say that an assignment is good if it does not have any unstable pair, or other words, an assignment is good or is stable if it does not have any blocking pair or unstable pair. This example is real. Okay, so given an assignment M, we have already said what is good for us, and we will just be dealing with whether it satisfies this notion of goodness or optimality, what we call. So we'll say that a matching is optimal or stable if there is no blocking pair with it. And our goal in this talk and talk about stable assignment. Right? So we are given a bipartite graph, we are given these preferences, and we are interested in computing assignments, and we are interested in asking whether there is an assignment or a matching. Okay. This is the same. Blocking pair or unstable. It's just another word. Or what I called as a problematic pair. Okay. Yeah, we'll come very nicely. Come to that. Yeah, so that I believe that the definition of a blocking pair, and therefore the absence of a blocking pair or an unstable pair defines a stable match. Right. So very natural questions that arise are the following. Given G an arbitrary instance, and remember, while in all these talks today and tomorrow we'll be showing very small examples, but the scale of the problem that we encounter in real life is huge. So you cannot just manually eyeball things. So we need to have a proper algorithm and an implementation which will actually automate all of these things. Right. So given an instance G of this problem, natural questions that arise are that is there a stable matching? I mean, does it even exist for an arbitrary instance, or for some instances the preference list can be arranged in such a way that however you find out or however you do the assignment, there will always be some problematic pair or an unstable pair. Right? So this is the first question that arises. And of course, if there is a stable matching, if one shows that there is a stable matching, how do you find that efficiently? How do you compute one? And then one of you asked, I think the question is it unique, right? Okay. Is a stable matching unique? That is, if the instance admits a stable matching, is there always one stable matching? And somebody had also suggested the size as being a measure of goodness. So maybe in this example, let us first explore the assignment that I have shown here is clearly not stable. But does this instance admit a stable matching? So we want to answer the question generically, but maybe we'll answer it for this example. Does the instance admit a stable matching? Yes. Sorry? A2 with B2, right? So instead of doing this large size assignment, maybe we can do a smaller size assignment and yeah, so the suggestion is to do this, and I think this is the instance, right? I did not change anything. Yeah, I believe so. And of course, given this assignment, one should again ask whether this is stable. For checking whether this is stable, it suffices to look at the unassigned pairs, that is pairs which belong to E but which do not belong to M, and ask whether they are blocking or unstable. So A2B1 is clearly not a blocking pair. A2B3 is not, because now A2 is assigned better. A3 is interested in getting assigned to B2, but B2 has taken somebody better. So therefore, this assignment is indeed a stable assignment in this example. So at least this example we have the answer that there is a stable matching, but we would like to answer this generically. And then, is this the only stable matching in this example, or is there any other stable matching? So in this example, it seems to be that the stable matching exists, the stable matching is unique, and it also says that the stable matching need not be max size, because the 3 size matching which is there is not a stable matching. So we would like to ask, how small can a stable matching be? Yeah, so yeah, that question is how large? I mean, so how large can a stable matching be? Yeah, match everything seems to be, yeah, a good bound, but I mean, it may not be possible also, right? For example, if I have an instance where It just looks like this. I have A1 all the way up to AN1, but there is only one post which is B1, and all these have edges. Then the upper bound that we are stating is N1, but that is a weak upper bound. So we can say that the smaller of the two sets, but again that need not be a good upper bound. The size of the largest cardinality matching is certainly an upper bound, because we are interested in matchings. So the stable matching can be as large as the maximum matching in a graph. So in that relation we are asking, but how small can it get? That is, can it go very, very small? For example, the largest maximum matching, or there is a large matching which matches 100 edges or 100 applicants, but then the stable matching is of size 10. Can this happen? Because we are imposing stability, do we have to compromise on size too much? This is a question that we would like to answer. In this example, I mean, it's a very small example. We are compromising in size by one vertex, but in general, what is the trade-off, right? So we will try to answer these questions in this talk. Okay. Any questions? Any other questions that somebody wants to raise? Okay. Okay. So what do people think in general? That is, given an arbitrary instance, will there always be a stable matching, or can there be instances where whatever assignment you do, there will not be a stable matching? Okay.
Sorry, I have a quick sanity check question.
Sure.
If you have an edge where both of them rank that edge at 1, you would obviously choose the edge, correct?
Yes.
That's right.
I mean, there is no way you can avoid that edge if you want a stable match. Yes, that's correct. Yes.
Suppose if like A, if any of the vertex from A is choosing some of the vertex from B, and the reverse is not true for any of the vertex, then A will not be matched. So if this is true for all the vertices, then there won't be a stable match.
Okay, so what you are saying is there may be instances where there is no stable match, right? So I invite you to just quickly construct a small example, right? If you can use your notebook and try to construct it. So are there other people who have some intuition whether it will be present or it will not be present? And maybe we can take a few seconds to kind of work it out, just one. Yeah, maybe everybody can work it out and just give a few seconds. Yes.
So there are only 4 vertices: A1, A2, B1, and B2.
A1, A2,
B1 and B2.
okay,
And A1 is only preferring B1.
okay,
Sorry. A1 is only preferring B2.
okay,
And A2 is only preferring B1.
okay.
And B2 is only preferring A2, and B1 is only preferring A1.
So this is the edge set of the graph.
So, like if like A2 is preferring B1, but B1 is not preferring A2.
So that we don't allow, okay. So I think maybe I was not clear enough. When we say that this edge is present, it means that A1 is acceptable or to B1, and B1 is also acceptable to A1. Only then we draw this edge, and therefore it also has to rank A1 and B, I mean the neighborhood, right? So you cannot draw these partial edges, that is A1 wants to get assigned to B2, but B2 is not interested. That is not allowed. Otherwise we cannot even solve things, right?
Then if there is a graph where there is no edge, then it won't.
Then it is empty.
Then it won't have a stable matching.
Okay, but sure, but there should be an unstable pair, but that unstable pair, that's why I defined it as an AB belongs to E, right? So it is a pair which it should be acceptable pair for it to block, right? Yeah. So
Here we are considering only finite graphs.
yes. And yeah, I said somewhere I wrote N1 and N2, and these are finite graphs. Yeah. Yeah. Any other?
So we can have a graph like this in the same graph.
This graph, right?
Yeah, in this graph, we just add the edge between A1, B1
Okay.
and A2, B2.
Okay, it's a complete bipartite graph.
Yeah, complete by that. Then we start our construction by A1 goes to B1 with priority 1. B1 goes to A2 with priority 2.
2. Okay, so that means this is 1.
No. B1 to A1 is
Okay,
No,
B,
sorry,
sorry.
B1 to A1 is 2.
B, okay, sorry. B1 to A1 is 2, yes.
And
Then this means that this is 2 and this is 1, right?
yeah.
Okay. Now,
Then
this you want 2.
yep. I just want to go circular.
Correct. So I believe you want A2 to be treating B1 as 2 and B2 as 1.
Yep. And then
Yeah, this the other way, 1, 2. Thanks. Okay, so let's look at this instance, right? So let's look at this instance and ask whether this admits a stable matching or this does not admit a stable matching. So there are only few things to do. So we should not look at the empty matching because the empty matching will not be stable. So I'll omit that. I'll also not look at matchings which are we have not defined, but these are not maximal. So I'll look at two size matching. So let's look at this just without loss of generality and ask whether this is stable or not. So whenever we are looking at A1, A1 does not have incentive to deviate or does not want to go to anybody better because it's matched to its top choice. So A1 cannot participate in a blocking pair. So we can actually write off A1 in terms of whether it is going to participate in an unstable pair. Is that clear? Right? Similarly, A2 cannot participate in a blocking pair or an unstable pair because A2 is also matched to its top choice. Is this clear? So, I mean, ideally I should have looked at A1, B2, edge and asked. Of course, B2 is interested in getting assigned to A1, but A1 is not interested in getting assigned to B2. Therefore, A1, B2 is not a blocking pair. Similarly, A2, B1 is also not a blocking pair. So, in fact, this matching, the red matching is stable, but very interestingly, you can also look at this black matching, which I'll give it in this way. And now let's ask, what happens if I were to assign A1 to B2 and A2 to B1? In fact, the roles of A's and B's are reversed. The A's are assigned to weaker partners, but B's are both assigned to their top choice. And therefore, the black matching, which is A1, B2 and A2, B1 is also a stable matching.
Because we can write off B1 and B2 because
Yes.
they have got their best
Yes,
preference.
yes. But I mean, it's not required to write off, but in this example, it so happens that we can just write off vertices and say that they do not participate in blocking pairs or unstable pairs. Yeah, so just to complete, this instance does admit a stable matching. In fact, it admits two stable matchings. And therefore, it naturally answers this question that a stable matching need not be unique. If the instance admits a stable matching, it need not be unique. We have an example where it is unique. We have an example where it is not.
It depends on the and in the definition of unstable pair.
And yes,
Exactly.
Yeah.
It depends on the and.
yes, it is and. It is not or.
Yes.
Yes. Yes. Yeah, thanks.
So stable matching is symmetric for A and B.
Yes, and we will do. We'll look at that. Yes, but we haven't answered this question. That is there a stable matching?
So in any unstable matching, always there will be two entities that will be dissatisfied. There cannot be a single entity.
Yes,
So suppose those dissatisfied entities can form a pair,
they are a pair, which is what is an unstable pair. Yes.
right? And like so they can form a pair, and then that will be a new matching. And we
Yes.
can go like that, and eventually we converge to a stable matching.
Yeah, so
That's
those
what we
kind of algorithms can be tried out. It's if not immediate how to work out those algorithms, but yeah, so we will, yeah, that's a nice idea. It's not immediate how to work out those algorithms, but we are still, I think you are trying to answer this in an affirmative way that there is always a stable matching, right? So we are going to do that, and in the interest of time, instead of going through that idea, I'll just say what a very celebrated algorithm is. So, okay, so I believe that the simple things about whether this instance admits a stable matching, whether there can be multiple stable matchings are all clear. Right? Okay, so what we are going to show is, and at least initially to me it was very surprising, that is every instance of this stable matching problem of, this is also called as the stable matching problem or the stable marriage problem. Admits a stable matching. Right? So whatever preferences you give, the two sets can be unequal, whatever edges you give, and you rank them in your favorite way, any adversarial way you want to do, and yet every instance of this of that problem admits a stable matching. So instead of just giving an existential proof, what we are going to give is an algorithmic way of constructing a stable matching. So it's a very simple and intuitive algorithm once you have seen it. So you start with everybody being unassigned or unmatched, and we call them also as free. So we pick one of the two sides. Both the sides are symmetric to begin with, but we pick one of the sides which we call as the proposing side. So this algorithm is attributed to Gale and Shapley, and it's a fairly old algorithm, 1962, but is in use, or its underpinnings are still in use in very important applications. And it is called as a proposal disposal algorithm or application rejection algorithm, where let's say the one of the sides, the vertices in the A side propose in some order and the B's accept or reject, right? So instead of writing down this algorithm, I'll just make a run of the algorithm, and then if required we can also write down the algorithm. Yeah, so the instance is clear, there is no assignment to begin with. Yeah, so this is the instance, and the A's start applying in any order to their, but just that they go in the order of preference, right? It's very natural for everybody to try out their first choice before going to their next choice. So let's say A2 decides to apply first. A2 goes and applies to the first choice, which is B1. At any point, if a vertex B receives an application or a proposal, it checks whether it is currently assigned to anybody. If it is not assigned, it will just accept. Think of a college, right? It is getting the first student. If it has one seat to fill, it will accept any student that comes in. But then later on, if it sees a better student, it is having the ability to reject the older student and accept a better student. So don't think of it in an actual process where students are going and applying and things are being accepted. This is an algorithm that is run in the backdrop, and therefore this is not like students going and getting rejected on arbitrarities. So A2 applies to B1, and B1 currently is unassigned, therefore it accepts this, and this is accepted or tentatively assigned. A2 is tentatively assigned to B1. After this, A3 goes and applies to B2 because that is the top choice, and B2 also has nobody, so B2 accepts it. After this, A1 goes and applies to B1, and B1 now sees that it has a conflict because it has tentatively given this or accepted A2, but it sees a better preferred application, and therefore at this stage B1 rejects A1 and accepts not A1, A2 and accepts A1. Is this clear? Okay, so therefore the current assignment, so this goes away and this has accepted A1, right? At this stage A2 has become free or is not assigned to anybody. So A2 again goes, there's no point in applying to B1 again because B1 is going to reject it. So A2 goes and applies to B2, and B2 is faced with the same conflict that B1 was facing. B2 has given a tentative acceptance to A3, which is a weaker partner, and therefore it withdraws that, this triggers this rejection. So this rejects A2, rejects A3 and accepts A2. So at this stage, what are the current tentative acceptances? A1 is assigned to B1 tentatively, A2 is assigned to B2, A3 is unassigned, but is there anything else for A3 to do? There is nothing because it doesn't find anybody else acceptable, and so the algorithm terminates.
And and like if we can prove, like we have to prove that if the algorithm terminates, it terminates in a stable matching.
Yes, yes. So, yeah, while I have not written down the algorithm completely, I would like to ask, is the algorithm clear to everybody? So, all the A's and B's are unassigned to begin with. A's start proposing or applying in the order of preference. B's accept or reject based on their being free or being currently assigned to any partner. Right? So one can write this down, but in the interest of time, I will just skip writing out that. And it should also be clear that the algorithm always terminates because every edge is visited at most once. In fact, as you may have noticed that A2 never made an application along this edge A2, B3. So therefore, some edges may not be explored or may not be made applications on. And therefore, we certainly get an assignment. This algorithm terminates and we get a matching. So now our goal is to show that this matching is stable. So the algorithm, I did not write the algorithm, but outputs a stable matching. Right? So, okay, so let us say that in an arbitrary instance, and we ran it on one example, but you could do this on any given instance.
So we have to, I guess, specify even if it doesn't matter at the end that in which order they're applying.
Thank you. Thank you for raising it. Very good point. I wanted somebody to ask. So why did I suddenly choose A2? Why did I choose A3?
Right.
Yeah. So in fact, we have all the vertices to be free. All the vertices set to be free. And whenever we have a choice, we pick a vertex arbitrarily. And we'll show a very nice property about that this arbitrariness or this non-determinism about which vertex we are picking does not actually matter. Right? But the side which is proposing or which is applying does matter. And in that small example, you can run the small example where we had two stable matchings. You can run it from the A side the way we described and run it from the B side and it will produce two different stable matchings. Right? So, thanks for asking the question. So, but before we go, so yeah, so the algorithm is actually not well defined if I don't say this. So, whenever there are multiple free vertices on the A side, you pick a vertex arbitrarily. The algorithm stops when either everybody is matched or the unmatched vertices have exhausted their preference list, that there is nothing more to do in their preference list or there are no more edges to apply to. Right? So, yeah. Okay, so 15 minutes are remaining or?
Yeah, before you break.
Okay, sure. So, that is my time.
After you can continue.
That, yeah, that, but 15 minutes I have, right?
You have another hour after that.
No, that, okay. Okay, thank you for the heads up. Okay, good.
Excuse me, ma'am.
Yes, yes.
Can there be maximum two matches stable?
Because you said that like it doesn't matter whether we start from A1 or A2, but it matters whether we are starting from A or B.
Okay.
So is there an upper limit of matching of two?
No, no. No, there need not be, there need not be only two stable matchings. There can be large number of stable matchings in an instance.
So maybe those that are not found by this algorithm.
Yes. There are stable matchings which need not be found by only these two. These two ways of proposing.
Is it because all edges are not explored?
In some sense, yeah. So, for example, yeah, in some sense, all edges are not explored by this algorithm. Yes. Yeah, sure. Any other questions? I mean, yeah, we can. Okay, so yeah, the number of stable matchings need not be. So, okay, so we'll quickly prove that it outputs us. The output that we get is a stable matching, and that is fairly, easy to do once you think about it for a while. So, yeah, let me erase this part only. So, while we ran it on this example, do not get stuck to this example. We have an arbitrary instance on which we have run the, we have run the algorithm from the A side which was making the applications. Whenever you had a choice, of choosing an agent A, you chose an arbitrary free vertex and it proposed to the next available vertex to next most preferred vertex to which it had not proposed. So I just want to clarify that let's say A2 was free at some point and A2 had a choice between 3 and 4, it will always choose the better preferred. I mean, it will make the application over the better preferred one. Yeah, you had a question.
We can observe that if the students are ranked uniformly among all students, then there exists a unique stable matching. So does the number of ranking sets that we have available has anything to do with the number of stable matchings we can different unique stable matchings?
Okay. That's a nice question. I don't know an immediate answer. It's a very nice question. Yeah, if there is a uniform ranking, yes, there is a unique stable matching. Actually, no. I mean, no, that is not true. You can construct examples which are disjoint and you can construct,
Just consider like two separate bipartite graphs, only which are individually uniform and keep flipping. So
you can construct large number of stable matchings with just 2 rankings. That same example that was given, right? Copy that again and flip the, I mean, in one of them keep,
So you have 2 to the power.
2 to the power, and that is kind of a way to generate large number of stable. Yes. Yeah, thanks.
We saw that we get a stable matching.
We did not see, we are yet to prove, yes.
Let's say like
You have seen it, right?
Okay. We know that there, let's just skip the fun. So does it matter on the run of like let's say for example if we just run the algorithm on A side, does it matter on the sequence of A's which comes?
Yeah, so in a few minutes we are going to show that it doesn't matter. Okay. Yeah.
Great question. It's a very nice question.
Yeah, it's a very good question. Yeah.
And we can do it just by contradiction.
Sure. I mean, yeah, we'll try to do that. But yeah, just for the sake of completeness, although you have seen that seen in the sense you have observed that the algorithm outputs a stable matching, we'll quickly prove this. So let's say that the algorithm outputs a matching which is this, and I mean, while I'm going to say that this is also matched, potentially this vertex could have also been unmatched, and let's say it forms a blocking pair. So there is this AI and there is this BJ, and let's say that AI, BJ, of course they must belong to the H set, they do not belong to the matching, and they form a blocking pair. That is, AI prefers BJ over its current partner, let's say BK, and BJ also prefers AI over its current partner, which is AK. If this happens, and although I have drawn this match list, this is not required, then let's ask how did this blocking pair arise during the course of the algorithm. So during the course of the algorithm, the AI must have proposed in its order of preference. So AI must have proposed to BJ before it went down all the way up to BK. So AI proposed to BJ, and the only way that AI is not assigned to BJ is either BJ was assigned at that time to a better ranked partner, or later on BJ got an application from a better ranked partner. And if you have noticed that throughout the algorithm, when we run it from the A's which are proposing, the A's keep getting, during the proposal sequence, A's keep going down in their preferences, the B's only keep on improving in their tentative partners. Right? So at the point where AI proposed to BJ, and at some point BJ must have rejected. So AI must have proposed to BJ, and BJ rejected AI, maybe immediately or later, for need not be for AK but for some AI prime, right? But what we know is that AI prime certainly lies better in the preference list with respect to AI in the preference list of BJ. And throughout the course of the algorithm, the B's only keep on improving. So its final partner is certainly is either AI prime, which could be AK, or it could be better than AI prime, which is AK. In which case, it is a contradiction to the fact that AIBJ is a blocking pair. Is this okay with everybody?
I'm just wondering one thing.
Yes.
If you replace that and by or, the existence won't be guaranteed anymore. But if the existence is there, then it will be unique. Is that true?
Okay. So that is a different way of defining blocking pair. So only A's can improve.
No, to make it an or, the only possibility is that everyone is both sides are getting just their top.
Just their top.
Yeah, so that existence is not
Triviality.
Yeah, but then that may not exist, right? And
If it
If it
exists,
exists,
the
yeah.
only thing is that you are in this utopia where A1 ranks
A1.
B1 as the top and B1 ranks A1
Yeah,
as the
but
top.
that is, I mean,
Yeah,
such a notion.
Yeah, of course.
Yeah. Okay. So how many minutes do we have? 5.
Another 5.
Okay. So I think I'll attempt to do the proof of this thing so that it may exceed a little bit.
Yeah, that's okay.
Okay.
You can finish the proof.
Okay. Okay. So I believe everybody is okay with that. It admits a stable matching. So we will come to that very interesting question that this order of proposals does not matter. That is, once I decide that the A's are going to apply, in whatever order I run this algorithm, and the A's keep applying, and I don't, of course, I never switch things. So the A's, whenever there is a free A, it selects the most preferred vertex to which it has not yet applied, and just applies, and then whatever the algorithm proceeds in that way. We want to show that this order is not does not change the output of the algorithm. That is, it always produces the same matching. And in the tutorial session, you can try that out on this example with different proposal orders. But we are going to show that the order doesn't matter. And for that, we are going to define what is called as an okay. So let's look at the matching from the A's side only. So let's say there are 4 vertices. This is the preference list, and each preference list could be of different length. But these are the neighbors, and this is the preference list. And of course, this is the top choice. This is the next choice, and so on. Right? So we have already seen examples in which there are different stable matchings. Right? So what I will do for every vertex is I will mark this vertex with a cross. If A1 can get, let's name this vertex, let's say B3, A1 can get assigned to B3 in some stable matching of the instance. For example, A1 in its preference list, B1 will be marked like this, right? Similarly, if I have not marked, let's say this was B10, and if I have not marked this, that means that A1, B10 cannot get assigned in any stable matching of the instance. So I keep just marking this, right? So whenever so if this cross, so I'll just put a square, right? So I just keep, and some vertices may not have any square in them. Like this vertex A3, it may not have any square because there is no stable matching that matches it. It remains unmatched. So these squares, is it clear?
Can you please define this again?
Yes.
Why?
Yes. So, okay. So let us say hypothetically that somebody listed out all the stable matchings in that instance for you. Right? So you look at a particular vertex A1 and ask, okay, do you get matched to this particular vertex B7 here in any of these stable matchings?
So the blanks are.
You can never get matched to this vertex in any stable matching of this instance.
Without the boxes, the blanks at the beginning where the B's in that order of.
Okay, so yeah, the blanks are in this order. So it is actually, so maybe it is for A2.
It's
It
B1,
is
B2, B3.
B1, B2, B3. But in this example, I will only put a box for B2.
Right.
Because there is a unique stable matching.
Right.
So therefore, the box says that this is, I mean, A2 can get matched to B2 only because that is the only stable partner.
There exists a stable matching where this match can happen.
This match can happen. Very good.
This
Yes. Yes.
matching can happen.
In our small example where there was a complete bipartite graph, A1, A2, B1, B2 and the orders were flipped, all the things were boxed because there were just two stable matchings and both of them are possible. So is it okay? Is the notion of this box clear? So whenever this blank is there, there is a vertex that is a neighbor, but it means that A1 can never get assigned to this vertex in any stable matching. Right? Okay. So what we want to show is that if you look at, remember that these vertices themselves are possibly different things. For example, here there is B2, this could be B2, this is B3, the B2 can appear somewhere here and so on. I mean, these are different vertices, right? So now, what we want to show is that the output of the Gale-Shapley algorithm, when A's are applying, gives us the matching in which for every A, we pick up the first box. That is, it is its best stable partner that is possible. Is the claim clear? Right, so I'll repeat, we are given an instance, somebody gave us all the stable matchings. How did they give us? Forget it. But they gave us all the stable matchings. Using that, I put these boxes. That is easy to do. And then the claim is that for every A, the output that is given is by this is just by picking up the first box. Right? Okay. So this is what we would like to show. So I'll erase the definition of a blocking pair. All of us understand it by now. So we just need a few things from the algorithm to be recalled and remembered. So whenever we say that, let's say that A is proposing to, let's say A2 is proposing to B3. Let us say it happens in some algorithm, in some sequence. What it means is that if A2 has any higher preferred neighbors, it must have proposed to all of them and they must have rejected it. This is something that is clear, right? So now, let us say that our algorithm does not produce this kind of a stable assignment, this stable assignment, right? Or we will actually show a slightly different statement, that is for, so let M be the output of our algorithm. In M, every A belonging to A is assigned the best stable partner. I mean, that is actually the same thing. Right? So this is what we want to show. So let us say that this does not happen during the course of our algorithm. What does it mean? That there is an A which is not assigned the best stable partner. It could have also been left unmatched by our algorithm, but then it has a better stable partner. That if it is assigned, it is assigned to somebody, or if it is unassigned, but it has a better stable partner. That is, possibly we assigned it to this box, but there is another stable matching in which it gets assigned to this vertex, right? Some other box vertex. So then, during the course of the algorithm, why did we not assign it? Because that vertex, for in this concrete example, if we did not assign A1 to B3, B3 must have rejected it. Is this clear? So then, our algorithm is actually just a sequence of proposals, acceptances and rejections, right? So we look at every proposal in our algorithm or application and ask, if you were an acceptance, that is it, the vertex accepted it, great. If you were a rejection, that is, let's say that AI applied to BJ and BJ rejected it, we call it a rejection, and we say that this rejection, or let's say, AI applied to BJ and BJ was initially assigned to some AK, so then BJ rejected AK and accepted, then we call this BJ AK as a rejection and AI BJ as an acceptance, right? So if the output is such that A1 was assigned to this box and not assigned to the best stable partner, then there must be a rejection of what we call as a stable partner during our algorithm, right? So write down your entire execution sequence, and your entire execution sequence is according to what you chose. I mean, so you had a choice between A2 and A3, you decided to choose A2 because both of them were free, but you fixed that choice, right? So you write your execution sequence, and that is well determined. It has nothing to do with this arbitrary choice. So you write down your execution sequence, and in that execution sequence, so let A to B be the first rejection of a stable partner. So if A1 applied to B2 and B2 rejected A1, we don't call this a rejection of a stable partner. We only call A1 B3, when B3 rejects A1, that as a rejection of a stable partner. Is this clear? Okay, so we have this entire execution sequence written down, and this A must have applied to B and B must have rejected it, and this is a stable partner rejection. Okay, so why did this happen? Why did this happen during the course of our algorithm? Why did B reject A?
Because we got some other information that was higher.
So B, this rejection either was immediate, that is when A applied to B, B was already assigned to somebody which is better preferred, or maybe somebody came in later and that caused the rejection of A to B, right? So whatever is that vertex, that is a higher preferred vertex, let's call it A prime. So it is a higher preferred vertex, and this vertex is what is causing the rejection of causing B to reject A. Is this okay? Now what do we know about where is this edge AB coming from? It is coming from a stable matching, right? Because A1 B3 is marked in this box because there is a stable matching containing it, and our algorithm failed to give A1 to that vertex, right? So let's call that matching as N. So our output is M. That algorithm, that we don't know what algorithm produced it, but that output is N. So let's ask, so this is an N edge, right? So this is coming from N, but our algorithm must have made this proposal, but B rejected it, and B rejected it because of this A prime. Now we will ask ourselves, where is A prime's N partner, right? Does A prime need to be matched in N? Maybe it is not matched, but if it is not matched, what happens? Every vertex, remember N is also a stable matching. So remember that this is an N edge, a stable matching which is supposedly produced in which A1 gets matched to a better partner than what we have. So N is stable. So with respect to N, B has a better choice which is A prime.
A prime B will become a blocking pair for N.
N.
For N.
Yeah. For N. Because if A prime is unmatched, then A prime B will block N. Is that clear to everybody?
Like vacuously, because it has no partner.
It has no partner. But also, it has no partner is not enough. B also prefers A prime over A, right? With respect to its N partner. Similarly, in A prime, if it is matched, it cannot be matched lower. Because the same thing will apply, because although it is matched, A prime prefers B over its N partner, B prefers A prime over its N partner, therefore AB block N. Right? So therefore, A prime's N partner cannot be here, it cannot be unmatched, and A prime's N partner must be above. So let's say B prime. Right? So now recall that we said that AB was the first rejection of the stable partner. We know that this AB rejection was triggered by A prime applying to B at some point. But if A prime has applied to B, it means that A prime has applied to everybody higher preferred before A prime can apply to B. It means that A prime must have applied to B prime and got rejected in our algorithm, which refutes the claim that this AB was the first rejection of the stable partner, because then we have shown you an A prime which gets assigned to B prime, which has a box better than what is produced by M. So therefore this first rejection of a stable partner does not exist, which means that there is no such rejection of a there is no rejection of a stable partner, which means that in fact if you pick up the first vertex here, it is indeed a stable, right? It is indeed the matching that we produce, right? So it gives us one more thing for free, that if you just look at the first boxed vertex in this way that I have boxed things, it is a matching, and it is the A optimal or the optimal, the asymmetric stable matching, I mean asymmetrically optimal, right? Matching that is produced, which is also called as the A optimal. And very naturally, if you run it from the B side, you will get a B optimal stable matching. And also that this A optimal stable matching is the worst thing that you could have gotten for the B's. If you would have drawn the same diagram for the B's with the boxes, you would see that for M itself, you get the last box in which the last stable partner, right? Yes. Yeah. So we asked, right? So where is the N partner of A prime? It must be matched, is clear. So if it is below, if I had this N partner below, then A prime prefers B over its N partner, B prefers A prime over its N partner, which means that AB blocks the matching in N.
In all this scenario, like, is it the assumption that we have the mappings, like what is the preference orders prior to start of the algorithm?
Yes. We know everything to the B.
Okay, so is it like, can't this work when the preference order is like kind of dynamic?
So it's coming in.
Yeah, let's say.
I mean, when you, okay, so, I mean, as long as when you need that, you know whatever, I mean, the next preference is known, it is okay, but.
No, if A and B both are coming dynamically and algorithm is also running.
Okay, so that is a different model, yeah.
Why can't A prime be unmatched?
Okay, so if A prime is unmatched, every vertex prefers being matched over being unmatched. So therefore, A prime prefers B over being unmatched in N, and B prefers A prime over its N partner. So A prime B is a blocking pair with respect to N. Yeah. Okay.
And,
Sure.
you mentioned that this A optimal stable matching is the worst for B.
Yes.
Can you repeat why that is?
Okay, so that is a small exercise, but I'll say what it means, and I think you can try to prove it. It just follows from this. So I'll just say what it means. So we write this B1 to Bn2, and we do the same technique with the same stable matching, right? I mean, we have all the stable matching, we mark them here. So instead of marking it on the A side, we mark it here. Our claim is that the matching M gives you this, the last box, right? Yeah, but it just follows from the A optimality. You can ask if a B doesn't get this and it gets this better, then you can prove a block. You can try it out. Okay, so maybe I'll stop here and oh, okay, yes.
Here, like we have seen from the way we either prefer A best partner and get B most partner over stable partner. So in the last scenario, this might be an issue that there is a concern that B is getting the worst label. So have we ever like come across a way to negotiate both of these?
Yes, there are in between stable matchings and something what is egalitarian stable matchings, and they can be computed efficiently.
This seems to be simple, so they must be complex.
Yeah, they're slightly more complicated, not very complicated, but you require a little more theory about the stable matchings. Yeah.
Just out of curiosity, in the JOSA allocation, so is it whom is the optimality more favored towards?
A student.
Okay.
Yes.
Yeah. That would be.
Yes. And in many cases, it's very obvious that one side gets the optimal, and it's typically for the student side where it is done. Yeah. And yeah, while this gives the theoretical underpinnings of the JOSA has many more things, complexities, and directly applying this doesn't work. But these are the.
And there's one thing that simplifies JOSA, that all the departments have the same preference.
Not all. Actually, all IITs have. All IITs have this one ranking. All NITs have the same ranking. But there are capacities, there are other quotas, etc. Right? So it complicates it a little. Yeah. Okay. Thanks.
Any more questions? Okay, we have a short break for tea and coffee. 10 minutes. on matching is by Professor Prajasta Nimborkar from CMI. She also completed her MTech at IIT Bombay and in the same batch as Professor Nasre. So they have more in common than just being stalwarts in this field. She completed her PhD at IISc Chennai before joining as a faculty at CMI. I have had the privilege of working with her on multiple projects, and owing to her exemplary work, she was recently promoted to a full professor. So congratulations. Please welcome Professor.
Thanks everyone for coming, and I would like to thank the organizers for inviting me here and giving me the opportunity to interact with all of you. Okay, so I will continue where Meghna left. So this place is visible. Okay, so just now we saw that every instance admits a stable matching, and there is also the Gale-Shapley algorithm, which gives us a stable matching, and it is the best for stable matching for the proposing side, and it is the worst one for the other side. Now we ask the question, is there anything, do they differ in size? So for example, if one stable matching is smaller and another is larger, then of course we would be interested in finding the largest possible stable matching. So as it turns out, it doesn't happen, and in fact all stable matchings are of the same size. So that is what we want to prove. We will in fact prove a stronger statement. It's not that all stable matchings are, it is true that all stable matchings are of the same size, but in fact they also match the same set of vertices. So we cannot say that, okay, I will find a stable matching where my favorite subset of vertices is matched. There is nothing of that sort either. If we want a stable matching, it is clear which set of vertices gets matched, and that is independent of the choice of matching that we make. Okay, so let me formally state this theorem. Is this font okay? Is it visible? Okay, I'll make it. This is visible, I hope. Okay, so this is what we want to prove first, and then we will see another interesting property of stable matchings. So how do we go about proving it? Any ideas, suggestions? How should the proof strategy be?
So we take two matchings in which
we take two stable matchings. Yeah, go on.
And the vertex was matched in the first one but not matched in the second one.
Yes, so let me call them M and N. And suppose there is a vertex. Without loss of generality, we can say there is some A vertex in A such that A is matched in M and unmatched in N. And somehow, of course, we will have to contradict this because the theorem statement is exactly against this. Now, what should we be doing to contradict this? Right, so we should say that one of the two matchings cannot be stable. Right, so we have to exhibit a blocking pair somewhere to say that one of the two matchings has to be unstable, and then our assumption will be false. Okay, so with that as template, let's try to formalize this. So let me start drawing. So suppose this is A, it is matched in M, and let's say in M it is matched to B. So this AB is an edge of M. Now A is unmatched in N. Can B be unmatched in N?
Be unmatched in which one?
N. So
If in the second matching both of these are unmatched, then we can say.
yes, so our assumption is that A is unmatched in the second matching. So B cannot be unmatched in that matching because they will both be unmatched in the second matching then, and they will form a blocking pair. So this B has to be matched. I will draw these second matching edges, that is N edges with dotted lines. And it has to be matched to something else because A is not matched in that matching. So let's say B is matched to A1 in N. Now how should the preference go? Between A and A1, whom should B prefer? We have to decide that. So can you think and say, figure out which one B should prefer?
We should prefer A1.
B should prefer A1. Okay, why?
Because if that was not the case, then let's say we are matching by the set B. We can do that. So then we would have queried A first, and then ABH would be present.
So actually we will not assume that this is obtained by any proposal algorithm. Okay, so we will assume that this is M and N are just two arbitrary stable matchings, maybe not obtained by any of the proposal algorithms. But on the other hand, look at A. So A is unmatched in N matching, right, the second matching. If B also prefers A, then this AB pair will be a blocking pair for N. Okay, so if it is like this, that is B prefers A to A1, if the preference is looks like this, there could be several things here and here. But if B prefers A to A1, what happens in the N matching? In N matching, B prefers A is unmatched, so A prefers B, then AB blocks N. AB blocks N. Or AB is an unstable pair with respect to N. Am I making sense? So B must prefer A1 to A, that is B's preference must go on this side. Now again, can A1 be unmatched in M? So A1 is of course matched in N to B. What about its other edge? Does it have an other edge or can it be unmatched?
It cannot be unmatched because B prefers A1 and A1 has only B, and M will not be a stable matching.
Yes. So second thing that we want to claim is that, so I am writing these small claims just to give a modular structure to the proof. Okay, so A1 should be matched in M, and what should A1 prefer? If A1 also preferred B1, then if A1 also preferred B, then A1B would be a blocking pair with respect to this matching. Right, so this is A match. So A1 must prefer. A1 must prefer B1 to B. Again, can we continue this same procedure? Again the same question, can B1 be unmatched in N? Okay, and why?
Because if it was unmatched, then we will, if it was unmatched, then A1, B1 would form a blocking pair.
Yes, so A1 prefers this. So if B1 was unmatched in the matching N, then this would be a blocking pair with respect to the matching N. Right, so B1 must be matched. By a similar reasoning, B1 should also prefer the partner in N over the partner in M. So B1 should in fact be matched and also should prefer. So B1's preference should go to the N partner and not to the M partner. Again we will apply the same reasoning, that is A2 cannot be unmatched in M because again this will be a blocking pair with respect to M. So this procedure will go on. How does it terminate? I mean, this cannot be an infinite path. So what is the way that this procedure will ever terminate?
This procedure will terminate when, say, our last vertex in the set B is, say, Bn.
Is?
Bn.
Okay.
So the last vertex.
So suppose this is the last vertex.
Yes. And we'll check that it will have matching only to some M, like to some edge in M or to some edge in N.
So it also has to have an N partner, right?
Yes.
But then again the same reasoning will apply and we will take this path further. But something different has to happen for this thing to terminate. I mean, we cannot keep on saying this.
Some preference has to be on A again.
Exactly. So something has to go back to the one of the vertices that we have already seen. But where can they go back? All these intermediate vertices have their M and N edges. They cannot get a new edge now. For example, B2A1 cannot be an N edge.
So only back to A.
Only way is to go back to A, but which says that if A is matched in M, A should also be matched in N. So our observation is that the path that we have drawn, it has the following properties. If the path, say it is A, B, A1, B1, A2, B2 and so on, every A vertex is has preference for the M partner, every B vertex has preference for the N partner. So every AI prefers M partner. Secondly, every BJ prefers N partner. And the path has to cycle back. The path must terminate at A with an NH. Okay, there is no, you can convince yourself that there is no other way for this path to terminate. It cannot end in an A vertex because then the last edge will be a blocking pair for M, and it cannot terminate in a B vertex because the last edge that is taken will be a blocking pair for N. So there cannot be a last edge for the path at all because it is always going to be a blocking pair. So the path in fact must be a cycle. And therefore A must be matched in M. Is this proof clear? You can ask questions if I have not made it clear enough. Okay, so we have then we have proved that every stable matching matches the same set of vertices. Consequently, they all must have the same size. So whichever vertices are left in one stable matching, they must be left unmatched in all stable matchings. Okay, so we will, yeah.
So by stable matching here we mean maximal stable.
What is maximal stable matching?
As in, like if we remove an edge, say a matched edge, the remaining matching will still be a stable match.
It will not be, right? Because for example, if you remove this AB edge from M, then AB will form a blocking pair because A and B both will be unmatched. So a stable matching has to be maximal because if an edge can be added, then that edge is blocking with respect to the rest of the matching. it again. A prefers.
What's A preferring there?
So A is matched only in M, right? Oh, okay, here. You mean when we close this, right? Okay, so when we close this, so what we see is A2 must be, B1 prefers A2, that is N partner. So A2 has to prefer the other one, otherwise this will be a blocking pair. Both will like each other compared to the matching M, and this will be a blocking pair. So A2's preference has to go to M, and then B2's preference has to go to N. Now if A also prefers B2, then again this will be a blocking pair because both B2 and A will like each other over the M partners. So A's preference has to go to B. So every A prefers the M matching, that is M partner, every B prefers the N partner, and this we can observe for any cycle which is formed by two stable matches. Now, so far it has been the picture that okay, there are a bunch of stable matchings in the given instance. Certainly one and maybe even more. But actually they have a very nice structure, a very nice relation among themselves. So we will go on to see that now. I will call the matchings P and Q so that there is no confusion with the M and N pronunciation. The M and N sound very similar. So let's say P and Q are two stable matchings. Any two stable matches, not necessarily obtained by our proposal algorithm or anything. We do the following exercise. So there is A set, there is B set. There are some P edges. These are all P edges, and there are some Q edges. Okay. Now every vertex in A, we ask the following question. Do you prefer your P partner or Q partner? We don't ask this to B vertices in B at all. We just ask this to A vertices. Okay. And whatever they say, so for example for this vertex A, we ask whether, okay, this vertex I have to draw an N partner, anyway it should be there, and so on. So every vertex we ask whether the vertex prefers P partner or Q partner. Whichever the vertex prefers, we just give that vertex that partner. Okay. Now what will happen? So give every A in A its preferred partner between P and Q. Not outside these two, only between these two. And we know that both of them should, everyone should have a P partner as well as Q partner because of the result that we just saw. So give every A its preferred partner from P or Q. What do you think will happen? Yes, so obvious thing is, why should it be a matching? Maybe A1 and A2 both like the same partner, and it doesn't result in a matching. Surprising thing is that this is a matching, also it is a stable matching. So I did not write. Okay, so this is a result. So at least this will give us a bunch of edges, right, when we do this. So call this set of edges R. And the claim is that R is in fact a stable matching. R is a stable matching. Again, first of all, we need to show that R is a matching at all, which is again not obvious. How do we show this? So let me draw a better figure here. So A1 is matched to B1 in P, matched to B2 in Q, and so on and so forth. And maybe something of this. Okay. So first thing we will prove is that this R is indeed a matching. So suppose not, then how should it look like? So suppose R is not a matching, then how does the picture look like? Maybe A1 and A2 both get the same partner, say B. Now, obviously they were not matched to same B in P or Q, right? So one of them must be a P edge, one of them must be a Q edge. So suppose this is the P edge and this is the Q edge. This is without loss of generality. But what do we know? We also know that A1 and A2 also were matched in the other matching. That is, A1 was also matched in Q, A2 was also matched in P. Right? So A1 had a Q partner, say B1, A2 must be having a P partner, which is B2. Because they are matched in both matchings, only thing is their preferred partner between P and Q matchings happens to be the same B. So what can we say about the preferences of A1 and A2 between their P and Q partners? So A1's P partner is B1, Q partner is, sorry, A1's P partner is B, Q partner is B1. Say it again. So how did we get this R collection? So suppose A1B and A2B both belong to R. How did they both land up in R? We gave A1's preferred partner between P and Q to A1, A2's preferred partner between P and Q to A2.
So
it happened to be the same B. Okay, so we are assuming that it is not a matching for the sake of contradiction. So what is the way it cannot be a matching? That means two of them get the same partner, because of which this doesn't form a matching. Now they also had a partner in the other matching. So let's say A1's P partner is B and A2's Q partner is B. Their respective other partners be B1 and B2. So how should their preferences look like? Yes, so A1 prefers B more than B1. Why? Because that is why we gave B to A1, right? Similarly, A2 prefers B over B2. What about B's preference? We can't say anything for sure, right? But then it has to prefer one of the two over the other. So without loss of generality, assume B prefers A1 over A2. There are other things, of course, in between. I am just writing the relevant things. Now can you see what happens?
Then in Q we have, then in Q we have band pair.
Yes. So in Q, B's partner is A2. So look at the Q edges, the dotted edges. B's partner is A2 and A1's partner is B1. But then both A1 and B prefer each other over their respective partners B1 and A2. Right? B by assumption prefers A1, A1 prefers B. So this is a blocking pair with respect to the matching P. Yes, sir. We don't know, but one of the two has to be the case, right? Either it has to prefer A1 over A2 or B1 over A2. So assume it prefers A1 over A2. If required, we can consider the other case another time. But when B prefers A1 over A2, what happens is A1B blocks the matching Q. Means it is a blocking pair with respect to Q because both prefer each other over the respective Q partners. Do we need to consider the other case when B prefers A2 more than A1? Yes. Right. So then A2B will become a blocking pair with respect to Q. So it is symmetric. But what we have proved so far is that R has to be a matching because two of the A vertices cannot get the same partner in R. Therefore, A1, A2 must get different partners in R. Can B1, B2 get the same partner in R? That cannot happen, right? Because we gave a partner to A's. When we asked A's about their partners, they gave a unique choice, right? We asked every A whether you like P partner or Q partner. So no A can get two partners because no A is going to say I like both. So A1 and A2 must get different partners in R. And so R must be a matching. Now what about the stability of R? We have not yet proved that it is stable. Okay, I think I will erase this claim or the proof. So I will write the second claim. We want to prove now that R is a stable matching in fact. Again, for the sake of contradiction, assume that it is not a stable matching. Yeah, sorry.
Must be the way we proved that R is a matching. So, did we first actually define it the way that we take in the edges where A is, like the edges are A with its most preferred partner, so that may have the same B, but do we discard one of them or how do we like?
Same B meaning?
And the case we were taking that A1, A2 have preferred the same B.
Yes.
So don't we already taken into the set R or not?
Yes, so this is the algorithm to get the set R. Okay, so our claim, we wanted to prove that R is a matching, which means every vertex should get exactly one partner. Here, the figure that we had drawn, B had received two partners, right? The picture was like this. A1, A2 both got B. Because of this, it was not a matching. No A can get two partners because this procedure itself allots it only one.
So then do we claim that we are making R a matching?
We are not making R a matching. This cannot arise because if this is the case, then one of them has to be a blocking pair. As in one of the matchings cannot be stable. Because see, B has a preference, right? So sure, A1 also likes B over the partner in the other matching. A2 also likes B over the partner in the other matching. These two edges cannot come from the same matching because this cannot be matching edges. So one edge comes from one matching, another edge comes from another matching. Okay, but they both like B over their partners in the other matchings. And now we said that depending on what B's preference is, one of them forms a blocking pair either with respect to Q or with respect to P. So it cannot happen that this procedure gives two of the A vertices the same partner. So every A vertex must be having a different partner in R, which means it should at least be a matching. Every stable matching is maximal because we cannot leave unmatched edges in, we can't leave endpoints of an edge unmatched in a matching. So if we have a matching like this, suppose this is a matching and then there is this edge where neither of them are matched, then this is itself a blocking pair with respect to this. Right? Because they prefer each other over their partner in this matching which is none. So every vertex prefers being matched to one of its neighbors over being unmatched.
Can this theorem be used to enumerate all possible stable matchings?
Yeah, so this actually gives a nice what is called as a lattice structure over stable matchings.
Okay.
So this can be used to prove that stable matchings form what is called as a distributive lattice. And the A optimal and B optimal stable matchings are the minimum and maximum in that lattice. So I am not defining lattice here. So, but then if you know about lattice or if you study it at some point, you will know that this actually gives a nice lattice structure. So there is a way to systematically go from one stable matching to another. Okay, so let's prove the stability of R. So is everyone convinced that this R must be a matching ring?
Yes.
Okay. Yeah, if at all there is any question, I will address it once we are done with this. So for now, assume, take it for granted at least that R is a matching. Let's come to the stability part. So suppose R is not a stable matching. So let's say these are the edges of R. If it is not a stable matching, there has to be some edge which blocks it. So suppose without loss of generality that these are R edges. And suppose A2B1 blocks R, because of which R is not stable. It can have many more blocking pairs, but this is one of them. Now what would happen? So clearly A2 prefers, because this is a blocking pair, A2 prefers B1 more than B2, right?
Just
Yeah.
one point. Why will this blocking pair have both edges in R?
No, the A2B1 is not an edge in R.
Sorry. Both vertices in.
That is why are they matched in R?
Why this blocking pair would have both vertices which are
Matched in R.
Yeah.
If they are unmatched, sure, this edge doesn't exist, but still A2 prefers B1 over R partner, right? Even if that R partner is empty, it is going to prefer B1. So even if it is not matched, you can say this is an empty partner that A2 got in R, and A2 of course prefers B1. And this has to be an edge in the graph in the first place. Yes.
Yeah.
So if there is a blocking pair, so suppose if there is a blocking pair, which means this is an edge in the graph, but not in the matching. So yeah, blocking pairs only are defined along the edges of the graph. If they don't prefer each other or don't have each other in the preference list, they don't form blocking pairs.
What I was asking is, what if the blocking pair was like A2 B4, where B4 is not matched in R?
You can give it a kind of empty partner in R, right? And say that still B2 is going to prefer A2 if A2 B4 is an edge. So if at all someone is unmatched, consider that that's an empty partner which nobody prefers. So A2 has preference like this because this is a blocking pair. A2 must prefer B1 over B2. But then how did we give B2 to A2? Yes, so this must not be A2's partner in either P or Q, right? B2 is A2's preferred partner from matching P and Q. So if this is P partner, then A2 had another Q partner which is somewhere later, or the other way around. So A2 prefers B1 over both P partner and Q partner because this B2 is its preferred partner from P or Q. But and also B1 prefers A2, which means this is also an edge either in P or Q, right? So A1 B1 either belongs to P or A1 B1 belongs to Q. Why? Because that is how R is constructed. A1 was asked, do you like your P partner or Q partner? It said, okay, I like whatever P or Q partner, and that happened to be B1. So A1's P or Q partner is also B1. So suppose this is the case. And now B1 also prefers A2 over A1 because our assumption is that this is a blocking pair, and hence this must be in fact a blocking pair for P as well. Because in the P matching, A2 gets something which is less preferred than B1, either one of these, and B1 also gets something less preferred, that is A1 as compared to A2.
So A2, B1 should be the blocking pair for both P and Q.
At least one of them. Maybe this edge came from P, then we can say A2 B1 is a blocking pair with respect to P. If this edge came from Q, then we can say that A2 B1 is a blocking pair with respect to Q. It depends on where this edge came from. So A2 B1 must block either P or Q. And this P or Q depends on where A1 B1 edge came from, whether it came from P1 or it came from P2. Alright, so I will stop. I think you can think about this and of course feel free to catch me if you have not understood or you have any leftover doubt. We also have a tutorial session where you will be solving problems, and I think that will give you more insight into blocking pairs and stability. So thanks once again. Let's thank the speaker once again.
Our next speaker is Professor C. Pondurangan, another alumnus of IISc. He is currently a Satish Dhawan Visiting Chair Professor here at IISc. He has not only served as faculty for over 35 years at IIT Madras, but also served as an institute chair professor. His work has spanned topics like cryptography, graph theory, and computational geometry. His talk today is on zero knowledge protocol. Please welcome Professor Pondurangan.
Thank you very much. Thank you. Yes. So how many of you are familiar with cryptography and its basic? Have you done some courses and stuffs like that? 1, 2, 3, 4. Okay. Very few hands. Okay. So that's an advantage for me. It's very difficult to address knowledgeable crowd. Innocent crowd, I can simply hack you guys. So Is it on? Yeah, now it's okay. So today I'm going to talk about one of the most brilliant ideas in cryptography. Cryptography is full of exciting ideas, concepts and principles. Basically it is trying to do something really impossible. Okay, and very specification of the tasks in cryptography itself is not clean like the one you see in mathematics. Okay, for example, if you take the problem of encryption, I have an encryption function. It will convert the message into a ciphertext. Okay, it should not be reversible by others, but it should be reversible by one person, the legal entity. The same thing, it should be invertible for somebody, it should not be invertible for others. Okay? So if you look at the clean logical way of looking at it, either a function is invertible or not. You have converted it into, so it's called, let's take f of x, f of message, encryption of the message, that is the ciphertext C. From C, can you get M?
Can you use the board to the right side of that hash?
This is okay. This is the cutoff point, right?
That is the cutoff.
Okay, so I will use here. So let's say encryption algorithm takes a message M and produces a ciphertext C. If the function is invertible, then from C you should be able to get M. That's the way to get, and it should be one-to-one so that in an unambiguous way you construct the message back. The fundamental challenge is this function should not be invertible for some people and it should be invertible for some people. How can the same function have both characteristics? Right? This itself you can see that mathematically little off from the regular math. There are several such things which are trying to achieve contradictory things simultaneously. It should be possible and impossible simultaneously. Okay? That kind of a challenge is pretty unique. Okay, that characterizes cryptography. Digital signatures. Okay? It should be verifiable and generatable by some, and it should not be generated by others. That's forgery, right? If your signature can be generated by others, it is forgery. So I need to generate this, I need a signing algorithm. Only I should be able to generate it, but nobody else in the world should be able to generate that. Possibility and impossibility is to be simultaneously achieved mathematically. Okay? And that's a very unique challenge. That puts the cryptography in a different league, even within math. The way in which it is trying to handle and do things in math is very different. Okay? So, what do you mean by this encryption algorithm is secure? Typically, in all math problem solving and algorithmic problem solving, you have a specification of a task. Right? You have sorting. You are given an input, the output should be numbers in the increasing order. And then you write a program and then you look at the output, see whether it happens. So there is a functionality and your logic is guided towards achieving the functionality. You write a program, you design an algorithm and other things. It's not just a functionality, it is not just a transferring, it should be secure. So what do you mean by secure? Security. Right? It should not be possible for somebody to give and see. It should not be possible for someone to construct. Yeah. All right.
The resources and time required to reverse it is enormous and inconceivable on a human time scale.
What's your question?
No, I'm just answering your question. Like, what does it mean to be impossible? So the resources and the time required to reverse the process would be inconceivable on a human time scale.
That is that's a two flavor in which we are going to address the problem. Is it mathematical impossibility or is it human impossibility? Right? Humanly impossible means it is computationally infeasible, which means you start working on it, it is going to take 350 years for you to invert it. I am very happy with the kind of invertible function. Okay? Mathematically it is possible to invert, there exists inverse and then you can compute in principle, but that's going to take 400 years, means I am very happy with that situation. Okay? That's called, therefore, impossibility, infeasibility. We need to distinguish between these two. In both, we need to have mathematical foundational results. Impossibility results are done normally in math. You do logical reasoning, proof by contradiction, you have various techniques of. But then infeasibility is a very tricky thing. That is addressed only by computer scientists. Because for mathematicians, either it is possible or impossible. Okay? They don't bother about resources, computers, memory, time, all of them are, okay? They can evaluate in principle 1000 by 1000 determinant, though 1000 factorial is very simply for mathematicians, it is 1, 0, 0 followed by exclamation mark. That's it. Okay? And in reality, for computer scientists, this is a dreadful number. This is a dreadful number. 20 factorial multiplication you can't do even with today's advanced computing, distributed, parallel, super, hyper, whatever the adjective you use the computers, you will not be able to do 20 factorial multiplications. It's simply not possible. Okay? This is computational infeasibility. Okay? You just trigger whatever is the computing resource you have to do this many computation, it will take more than 1000 years to finish the task. Therefore, even 20 by 20 matrix determinant as defined by mathematicians we cannot evaluate in real world. Okay? So this is the computational infeasibility. Things like typically 2 power 80 steps, computationally infeasible. If there is an algorithm or if there is a process that requires 2 power 80 computations, in today's standard, it is declared as computationally infeasible. Therefore, 2 power 128 step I need to solve this problem means I will be very happy to leave that problem as open to you because you will not be able to get the answer. 1 second, I will just switch off this. Yes. Okay, these are all computational infeasible limits. 40 factorial. I can't deal with this many steps of computations. Okay? So, and when we are trying to solve these kind of problems, we, in the cryptography, they start with the basic notion of one-way function. This is a part of a paradigm in cryptography called the public key cryptography. In public key cryptography, we have a one-way function, that is f of x is easy to compute, but given f of x, finding x is computationally difficult. That's what we mean by hard. In computer science, you have notions like NP completeness and there are complexity classes and there are various ways to say things, but I will use a simple English word, computational infeasibility or hardness. If it is computationally hard means practically you just cannot solve that. Okay? And then get an answer. Therefore, this is called the one-way function. One-way functions form the core of public key cryptography. On the top of one-way function, we build something more. If it is a one-way function and if I simply use this for encryption, it's one-way function, right? It is infeasible for anybody in the world, everybody in the world. But then how will somebody invert it? If I use a one-way function as an encryption function, then from C you can't get M. Therefore, what we need is one-way function with a trapdoor. There is another information plus another information given f of x, finding is easy. So this hard and easy is the word for computational feasibility. Right? It will be very easy to I'll give one just additional information. This is called the trapdoor. This analogy comes from our real world example or real world scenario where in our home most of us will have a chain attached to the wall and there is a pad with a loop and that chain will have a nail head. You can easily push the nail head through the loop and then lock it. Others cannot unlock it. Outsiders will not be able to unlock it. But the owner of the house or the person inside the house can easily take it through the loop and then pull out the chain. That's a trap door. So it is impossible for outsiders, possible for insiders. Asymmetry. This asymmetry is fundamentally very important for cryptography. There are two things that are important, this asymmetry and the second one is the randomness. Randomness is really, really important. The computational infeasibility is also going to be examined in the context of randomness. Most of you would have heard the password cracker, okay? If somebody is hell-bent on breaking your Gmail password, they can do it in 10 minutes. We do that in IIT Madras for fun. Just like that, you ask them to you set your password and then I will crack it in 10 minutes. Okay? Simply possible. I don't have to use even sophisticated tool. Anybody's password over here, we can simply break in 10 minutes. Max 10 minutes. Sometimes I will be able to break in even 1 minute. Alright? Therefore, my Facebook account password is maintained by my undergrad student and not by me. Okay? So why I should keep one and then ask them to break it? You guys maintain my FB account. So that's what is done. 2010 batch students are maintaining my FB account. Okay? So we used to do all of them because the point is that, of course, your password must have 8 characters and lower, upper and all those things. But nobody tries to break your password like, is your password A or B, C? No. Then I try. Do I try like that to break the password? Definitely I don't do that. Okay? So we use randomness. We use lot of additional information that is reducing the uncertainty. Right? The rapid way in which we reduce the uncertainty using randomness and all, we are able to simply break that. Therefore, the decryption, I mean, discovering the M, although you have a one-way function, it could become easy if I use randomness and some allied information, if some related information and other things are there. So, given f of x, finding x should be hard even if you use randomness to find, even if you have some related information. Right? That's what we mean by hard. So, even if you randomly try, that's why the randomized algorithms form the core of cryptography. In other words, the computational infeasibility is defined in terms of the probabilistic algorithms. What the probabilistic algorithms will do is, it will use randomness and then make random choices and then it will explore the possibilities of solving the problem. Sometimes this random attempt might quickly give the answer. So your expected running time could be polynomial. We know that in computer science, the great divide is polynomial, non-polynomial. If it is polynomial, efficiently solvable. If it is non-polynomial, it is hard. So that is the rough dividing line we have. So expected running time, if it is a polynomial, if I have a randomized algorithm, its worst case may be a pathological case that may be exponential. That really doesn't matter for me. If I am able to, with a decent probability, crack the problem, or if I am able to get with a decent probability given f of x, finding x if it is possible, then it is not qualified as hard. So the qualification of hardness is done not actually in terms of NP completeness or NP hardness, it goes a little further than that. Even by a randomized algorithm, even the expected polynomial time, even if some additional allied information is available to you, it should be very difficult for you to invert. That is the one-way function. And with that kind of one-way function, but I give one small piece of information, everything becomes easy for you. And that is called the secret key. So the possessor of the secret key will be able to invert. The guy who doesn't have the secret key will have his life very hard. Okay? So that is the one-way function, beautifully defined. Okay? Like the mythical character with lots of attributes, power and character, we have defined it. Do we have one-way functions? Right? It's as expensive to answer this like $1 billion question, like NP completeness and so on. We really do not have concrete one-way functions that this function is one way. Nobody has proved it. I would love to have one such one-way function for my cryptography. Unfortunately, I don't have that. What I have is something like one-way function. Okay? They are called number theoretic. They are called hard problems or reference hard problems. There are certain problems which are like one-way functions. Okay? Till now, nobody has found out a way to do that in polynomial time. We believe it can be used as a one-way function. It's called the firefighter principle. Right? What firefighters will do is that do the best. The instruction for them is, if you can't do the best, do the second best. Okay? So ideally, I would like to have one-way function, and if I do not have that, take something which like one-way function. So I'm going to introduce you a one-way function which is a classic one-way function, and that's foundation for most of the practical things that are currently used. Okay, various encryption standards, digital signature standards, blockchain, security in your transport layer, you name it, it's all used. Okay, so one such problem I'm going to tell you. All you need to know is to understand multiplication and division and remainder. That's all you have to know to understand this one-way function. Alright, so let us take a prime number p, say 11, and then take a number 2. Let me list the number powers of 2. So 2 power 1 is 2, 2 power 2 is 4, 2 power 3 is 8, 2 power 4 is, well, we are in the modulo world now. That's what I want to tell you. That is, we are not going to use all numbers, we are going to use numbers in the range 1 to p minus 1. So 1 to 10 I am going to use. 2 power 4 is now therefore 5, because it is 16 actually, but in the modulo world you take a remainder that gets you 5. 2 power 5 is 10, 2 power 6 is again 20, goes to 9, and 2 power 7 is 7, 2 power 8 is 3, 2 power 9 is 6, and 2 power 10 is 1. That's beautiful, right? So from 1 to 10 all numbers are figuring out, and if you multiply further by 2, you are going to get again 2 power 11 will be 2, 2 power 12 will be 4, it's going to cycle. Therefore this is called a cyclic, well it is also called a group, cyclic group. Why I am calling it as a group? It will satisfy all the group theoretic group axioms, abstract group axioms, it will satisfy. Okay, it is closed under the operation, it has an inverse, it's associative and commutative, it's all nice properties you will have. Okay, so it is called the cyclic group. And the 2 is called the generator because it generates everybody in this selection, in this collection. 1 to 10 is figuring out here. If you use 4, that's not going to happen. 4 power 1 is 4, 4 power 2 is 5, 4 power 3 is 9, 4 power 4 is 3, 4 power 5 is 1. It starts cycling now. Again it will be 4, it's a cyclic subgroup, a smaller set, right? That's also a cyclic subgroup, but it doesn't generate everybody. This 2 is generating everyone, and then 4 is not generating everyone. Doesn't matter. Let us consider 2. Okay? Since every number is generated by 2, take any number in this, right? Y belong to this set. There must be a x such that 2 power x equal to y. Every number is generated, there must be some x. And that x, we borrow the terminology from continuous world, is called a discrete log. Right? because 2 power x is y. So what is x? In our normal world, it will be log y to the base 2 will be x. We call it as a discrete log because this is in the number theoretical world only integer, and that too in the modulo world, not in the real numbers and not even in the full integers. So we call this as a D log. Okay, discrete log. So given y, what is the discrete log? That x with respect to the generator and y. Therefore, for example, what is log 5 to the base 2? Log 5 to the base 2 is 4. But remember, this is in the modulo world 11. In the modulo world 13, it could be different. In the modulo world 17, it could be different. And it all depends on the generator. Now, let us generalize this. Let us consider G to be a cyclic group. G, a cyclic group generated using a prime number P. Okay, and we have G is a cyclic group generated by G and using a prime number P. Okay, therefore all elements are generated by powers. G is in fact G power 1, G power 2 up to G power P minus 1. All of them will make up this G. This is called the cyclic group. In this cyclic group, the discrete log problem is qualifying as a one-way function. Given x and G, I can raise G to the power of x easily. Right? We have a very simple algorithm, doubling algorithm, which in logarithmic number of steps or in polynomial time, you can find y. But given y and G, finding x is extremely hard. No one has found out a polynomial time algorithm for it. Even randomized polynomial time algorithm is not available. Absolutely miserable situation. Right? But then this is what cryptographers are going to use. They will leverage on this. Okay? Discrete log problem in the cyclic group is hard. There are certain groups on which it could be easy. Forget it. There are excellent number of groups on which this is hard. Okay? This hardness is what we are going to use. We need a one-way function, and we need a one-way function with a trapdoor. All these things are needed. Okay? We will not get into that. We are going to focus on another problem called the zero knowledge protocol. But this we are going to use. Discrete log problems, hardness is used. Okay? Cyclic group, generator, discrete log problem. That's all you need. Always remember this example. Okay? And this also you should remember. We will refer to that if time permits later. Otherwise, it's enough if you remember this. Okay? That's all we need. Now we can state a problem that we are going to address. This zero knowledge protocol is Turing award winning idea. Turing award is given by ACM. It's the highest award given for computer scientists, right? For the accomplishment, for an idea that they generated and stood the test of time. It should influence the subject for more than a couple of decades at least. And then it should open up a sub-branch and then coming up with a completely new way of thinking. That kind of an idea. Okay? Like the notion of gravity before and after Newton. Okay? And then law of conservation before and after. So you have plenty of great ideas, extremely great ideas. Like notion of entropy before Shannon and after Shannon. You have phenomenal great ideas generated by mathematicians and researchers. One single idea that can completely change the complexion of the way in which you think in that area. Zero knowledge protocol is one such idea. Okay? I'm going to explain that idea and what it achieves using this problem. Okay? The objective is the following. You have to identify yourself. It's called the identification problem. How do you identify yourself to your Gmail server? You type in your Gmail ID. Okay? Everybody has a Gmail ID. Your friend also may know your Gmail ID. He can also type your ID. But then the Gmail poses what is known as a challenge. Give me your password. Prove that you are yourself. Then what do? you type your password. Even if you type your password wrongly, it is going to reject. It doesn't know who is actually typing. But it is looking for a proof. Right? Therefore, the prover must give the credential. Ideally, it is something unique that only you know. Okay? So, identification is the unique information you have. Typically, identification is a unique physical feature you have, like your ID photo, or you go to some sophisticated entry port. You put your finger, right? Your digital recording of your finger or iris. So, these are all the unique way in which you are identified by the system as it is you. But now, you are the unique information that you have. Just the unique information. That's called the password. If that information is known by others, he can impersonate easily. Suppose your friend knows your password for your Gmail account. He can also log in, type your Gmail ID, type the password he knows. He will also access your mailbox. Absolutely no problem. Right? Therefore, the secrecy or security or the identification of the uniqueness depends purely on the secrecy of the information that is uniquely associated with you. You are the unique information that you possess. Right? What do? You type the password and then it goes to the other end. This is called full disclosure proof. In full disclosure proof, the prover gives the credential explicitly to the verifier in full. Right? The whole password goes. If somebody hacks your password, they can really do the replay attack. Even he need not know what your password is. The same bit pattern, if he sends it across to the system, then he may be able to impersonate like you. Okay? And the sources are need not be even people. Both of them could be system. You take ATM machine. You have a ATM machine and the bank server. ATM machine sends your PIN number, encrypted or plain, whatever it is. It simply goes to the other end, from system to system. So there are two parties, prover and verifier. There is a prover, there is a verifier. Prover has to prove that he is the person, but how is he proving? He says that he is the person who has a unique information. That's what called a secret key. And the person who knows the secret value. Nobody in the world knows. That's what he says. The verifier says, prove it. And then if that person gives that information, the verifier will be able to verify. But then the problem is, now verifier also knows the secret information. Right? Your password is stored in somewhere, some system. If that system is hacked, you are ruined. Okay? And that's what is happening. You might have heard about a lot of horror stories. Okay? 1 million Visa account privacy is compromised. Okay? What happened to all that data which was there, encrypted or whatever it is? That system is compromised, and then the storage there, somebody has cracked the whole thing, and now all the financial transaction you have done is known to some third party through Visa card or MasterCard or something like that. The whole thing is that the secret information is stored somewhere and that is verified. So, verifier already has something, the prover sends it. There are two dangers here. One, a hacker can get it, or if the verifier is malicious or compromised, again, all the thing about your uniqueness is lost, secrecy, everything is lost. But the full disclosure proof will always have this difficulty. You have to send it. The bank ATM machine has to, you are withdrawing the money from, let's say, Mumbai. Your account might be in Chennai. But there also you are able to withdraw. So the point is, it has to be sent for verification. But the full disclosure proof has got major difficulties. One, it can be traced by an attacker. Two, if the other system must have already a copy by know your customer or in the system establishment time, or when you are logging, when you are registered with the system, you create a password, it should be all there. So it is there out. Although we believe that it is safe, it may or may not be safe. These are all the problems. Therefore, these people have come up with, Shafira, Goldwasser, Mikali are the guys who come up with a beautiful way. I will prove the credential. I am the so and so person, but I am not going to store the information anywhere. The secret is not going to be available. Secret will not be shared. Secret will not be sent. Nothing. Okay, but I am going to convince. How it is that you are going to convince somebody that you have an information without giving that information? That is zero knowledge protocol. Okay, zero knowledge, no knowledge, nothing will be leaked about the information you have, which is identifying you. Right? Beautiful idea. Full disclosure proof is give that information. Putting us into this context, we will identify a GP and let's say I select a random X and compute X is a secret key, sorry, Y equal to G power X mod P. This I compute. This is my public key. Y is public. G, P, all are made public. I tell the world that I am the only person in the world who knows the discrete log of Y. Of course I know, because I only created X, I computed in my room, and then I have got the Y, and then I know that. Right. Somebody says prove it. What is a full disclosure proof? Giving X to that person. Then that person can compute G power X, it will be Y, and he knows that yes, I know. But then now what is the problem? That fellow also now knows. He can go on and impersonate like me. He can also claim that I am pondering. Of course, I am not a big person, nobody is going to impersonate me, but if that is the X of Bill Gates, everybody would like to use that they want to prove that they are Bill Gates and withdraw some $1 million from some account. Okay? So the point is, this X is known, and X is the secret key, Y is the public key, and discrete log of Y is known to only one person. So he has to prove that he knows the discrete log of Y without giving X. With giving X, that is easy. The verifier is convinced. Verifier, now how do you convince verifier that the discrete log of Y is known but without giving X? This requires a three-stage protocol. The previous protocol, which you have used to prove yourself, is called challenge response protocol. The computer challenged, Gmail server challenged you, prove that you are pondering. I give my password, response, it is verified, and then it accepts, and then it opens up my mailbox to me. Okay, that is called the challenge response model. Now, the challenge response model requires full disclosure. I am not going to do that. Therefore, I am going to enter into a three-phase protocol, and this is called commitment challenge response model. This is called the Sigma protocol. Okay, this will involve interaction in the following way. There will be a commitment which will go from here to here. There will be a challenge which will come from V to P. There will be a response from P to V, and then there will be a verification, and there will be a yes, no will be concluded. Okay? This is called zero knowledge protocol. This is structure. We will prove the zero knowledgeness, everything soon. Okay? So, this is what is going to happen. If I have only these two, challenge and response, the challenge is this and response will be disclosure. That if I want to avoid, I need to have one more phase, and that is why we have a commitment, challenge and response protocol. This commitment challenge protocol can be easily and very elegantly understood with an example, and this is called the quiz quarter paradigm, cave paradigm. Quiz quarter cave paradigm is going to explain something which is going to be mathematically realized soon. Okay, here is the quiz quarter paradigm. There is a cave, circular cave. Okay, and there is a gate. This gate cannot be broken, or it just cannot be, you can't do anything with respect to this gate which is there. Okay, the only thing is that gate can be opened by a mantra. Okay, you can chant, even you can meditate that mantra, you don't have to even loudly say. Okay, say it's abracadabra. Okay, so you say abracadabra even mentally, standing here or here, it doesn't matter, the gate will open. Other than that, there is no way to open. Okay, this is the setup. Now, there is a guy who knows the mantra. Let's say I know the mantra and I claim I am the only person in the world who knows this mantra. So, how to prove that to a verifier? Full disclosure proof is I tell the mantra to him, he walks into the cave, he chants that mantra, the gate opens and he is convinced. But now he can also impersonate and then this is a full disclosure proof. That's not going to be done. Now, what will be done? First, a commitment will be done by the prover. Prover comes, walks into the gate, walks into the cave, either he goes to this or, so let us have the following convention. This is right, this is left, okay? I write like this, right and left. So he has gone and then settled it down to the right side of the door, alright? So now verifier comes here. Verifier comes here. Now he is going to give a challenge. He is going to give a challenge. Appear to my right. Okay, appear here. Now no problem. Even without chanting the mantra, this fellow can go here. But suppose he says, appear to my left. Appear to my left, he says. How can this fellow go to the left? He must open the door and then he must appear here. If this fellow is a genuine guy, he will be able to do that. Otherwise, he will be caught. But a genuine guy can chant the mantra and open the door and he can correctly respond. Now, you see that V is now convinced that he might have, but then there is now a probability of half. A cheater can get away with the following thing. He might have gone to the right, we might have also asked to come to the right. He might have gone to the left, we might have also asked to come to the left. In these two cases, even an impersonator will win the protocol or successfully give a correct response. But he is going to be caught with probability half. Why? He may go here, but we may ask to the right. Notice that when the commitment is done, he doesn't know what the challenge is going to be. He can't pre-prepare himself to fool the verifier. The verifier, this is where randomness is crucially used. Verifier's challenge is going to be a random challenge. And the impersonator cannot prepare himself in any manner. It's perfectly random. Therefore, he is going to be caught with probability half. But a genuine guy will always pass the test. The impersonator is going to be caught with probability half. This asymmetry, we are going to leverage on it. Let's play this game 20 times. What is the probability that an impersonator is capable of fooling the verifier all the 20 times? Every time it is independent. Every time he chooses a way to do the commitment, the challenge is random and then he may be caught in. So it's only probability 1 by 2 power 20. Right? It's only 1 in million that he can fool. Otherwise he just cannot fool that. Right? He will be caught. He will be caught with overwhelming probability. Okay? Impersonator. So this what low probability event are considered as impossible event. Very low probability. 1 by 10 power 6 is practically, it is not something that you are going to care about. Right? That's the probability of winning of an impersonator. But an honest guy will always win. Whatever the challenge, correctly he will answer. Appear to the left, yes, he will appear to you. You ask appear to you, you walk, chant the mantra and then, if necessary. Therefore, he will never fail. But he is going to fail overwhelmingly. And that is the asymmetry without revealing what the mantra is, right? A protocol is going to verify whether the person is genuine or not, and it is going to work with overwhelming probability. So, like computational feasibility in randomness, high probability events are sure events. What should be that? Or low probability events are never going to occur event. So, the limit is something like this: 1 by 2 power 30, 1 by 2 power 40. These are all very low numbers that any event with this probability will be considered as a zero probability event. We will work with that assuming that it's not going to happen. Yes, mathematically there is a probability that a cheater can get away with it and he may convince verifier that he is the person who knows the mantra. but the probability for that is so low that in practice, okay, it's not going to happen. Therefore, you are going to use several rounds of this interactive protocol, and if he wins in all the rounds, it will be deemed as the person with the appropriate authentication, and he will be let in, or he will be accepted. Notice that there is a very small probability, but that probability is so small that, to give you a simple idea, what is the probability that when you walk on a rainy day, you will be hit by a lightning and you will die? There is a probability, right? There are rains and then lightning and then the area of a rain, number of people walk, you walking at that time. Put all the probability, multiply, assume that all of the, you are going to hit a small number, but that small number is not smaller than this. But then, are we conscious about that when we walk on the rain? Or we always fear that if I step out, will I get hit by a lightning and then would I die? And the reason is, we are convinced that, while that is, there is a non-zero probability, okay, you do hear in the newspaper, right, lightning hit the one and cow died and this died and her, but got burnt, all of them are happening. But the probability is so low that you practically treat that it is not going to happen. So, impersonator will not win. Genuine person will always clear. The advantage is now nobody knows what that mantra is. And no one can replay attack. Suppose somebody observes, they put a camera here. An attacker puts a camera and watches one successful round of. Can he get the ability to win just by seeing that recording? Can he now enter into the game and then win? No, because every time the challenge is random. Even if he tries to imitate, he is going to be caught. Right? The choice is random. Therefore, it is not possible for a third party who is observing the protocol, who is observing the interaction, data exchange, and there is, this secret is not stored anywhere outside, it's only with the owner of the secret. Zero knowledge protocol. Nobody gets any idea, but I am convinced that I have that information. Alright? I am convinced that I know the mantra by playing 20 times, and in all the 20 times I am the winner. The reason is, only a person who knows the mantra can win all the 20 times. Okay? And this is called the round complexity of zero knowledge protocol. In how many rounds you have to play to get a desired level of probability? It's an interactive protocol which will go in rounds. Okay? A lot of research work is done on the round complexity and the accuracy with which you can win and all those kind of things. Beautiful math is there in all of them. Here in this protocol, 20 rounds are needed to get an accuracy of. We will see now what's going to happen. What's the mathematical analog of that? So there is a commitment, challenge and response. Right? Now the commitment. Prover is going to choose a random value k between 1 less than k less than p minus 1. Chooses a random k, and after choosing a k, he is computing g power k mod p and sends g power k. All computations are mod p. Okay, so he will send g power k. This is a commitment. Like getting into the cave, he has already committed. This he has to do. Alright? Now, V is sending a challenge, a number E, that is also 1 less than E less than P minus 1, a number is sent as a challenge. Now, P is going to generate a response. What is that response? Response is yes, and yes is equal to, right? Yes is equal to K plus EX. What is X? X is a secret key. X is a secret key. P is the person who has X as a secret key and Y as a public key. The relation between X and Y is known. These are all known. Y is G power X. X is not known, but Y is G power X is known to the world. And the person is claiming that I know X, and here is the corresponding Y, and I am the only person in the world who knows. Now this protocol is played. Yes is sent. Now, what is the verification that is done? The verification done at the other end is, look, what is the property of S? What is G power S? G power S is G power K times G power Ex mathematically, that is equal to g power k times g power x whole power e, and g power x is y, g power k is y power e. G power k is known to the verifier. This is the commitment, right? This is the commitment. Y is the public key. E is the value generated by V. Therefore, V can do this task. He has got S. He can compute G power S. He can compute G power K. He can compute Y power E. Right? And he can check whether these two are equal. If these two are equal, you accept. That is the verification. If they are not equal, you reject it. Now, because if this is not equal, they are going to reject. Look at the predicament of an impersonator. Suppose a guy is trying to say that I know the discrete log of y. Okay, play. The verifier says. So, we call the impersonators in P star. If you go to the research papers, the notation used. So P star is a guy, he is impersonating. First step he can do. He can also choose a random k and then he can send that. And the next step also happens. We also sends E. Now comes the question. How is he going to generate this yes without knowing x? He doesn't know x. Right? He doesn't know x. But then he has to generate a yes which will clear this test. He has already sent g power k. He has already sent g power k. But how is he going to get an s such that g power s is g power k times y power e? How is that possible? E is sent by him, it is not cooked up by him. Right? There is no way he can do that. There is absolutely no way he can do that. Right? Because there is only one value and the P here is not 11 kind of a P. If you choose P as 11, even school dropout will break this system. Okay? So your P should be something like 2 power 256 of this size. Size of P must be something of this kind. In that case, the X that you have chosen without knowing that, generating an yes, he will fail. He will fail with overwhelming probability. He can try a random yes, assuming that yes is going to be k plus e, but it won't be because it is a probability 1 by 2 power 56. You choose a random value, you don't know x and you want k plus ex is to be generated. K is fixed, e is fixed. Without knowing it, how will you get an yes that would pass this test? So you will fail. Impersonator will fail. Impersonator will fail with overwhelming probability. Right? So you can play 2 or 3 rounds and then you can convince within that itself it is going to be a the probability of 2 power 256, 512, like that it is going to fail. Because this E is also random. Every time this will be different. The P star can choose any K. It doesn't matter. But K plus Ex must have that unique value. There is only one value for which this would be true. For other values, it will not be equal. So the test will fail. What is the test done by the verifier? Here, what is the test done? Have you actually appeared to my right or not? Here in mathematically, you are going to check an identity. This is an identity to be satisfied by the correct yes. This identity will not be satisfied by any other yes. Therefore, any other junk, if we sent as a response, it is like feeding wrong password or something like that, it will be rejected. Therefore, impersonator will not even try to play here. He knows for sure that he is going to be caught. What is the point in even entering into the protocol? Right? But assuming that he goes through the protocol, he is going to be caught, and this is the zero knowledge protocol. An honest person can always win. Now, let us pause for a minute and then see. His secret key safe? Is the secret key safe? Yes, he is sending. E is sent by verifier. Yeah, we will, don't worry about it. They have to wait until the seminar is done. Okay. So, E is sent by him. K is also, well, K is selected by this guy. But is it possible that you have, is anything leaked by, is anything about X is leaked by yes? I'll give a simple example to connect, and with that, the 10-minute bound also can be respected. I have a number in my mind between 1 and 100. What is that number? No. I can keep saying no. Because you are going to make only a random guess. Alright? Now, I have a number in my mind, X. I have added a random number. That random number could be positive, negative, 0, and the answer is 40. You are seeing now 40. Now, what can you say about the number in my mind? Can't say again, because it could be positive, negative. My number could be 1 and the random number could be 39. My number could be 70 and the random number could be minus 30. Therefore, I told you it could be positive, negative, 0. Therefore, the point is you are not able to say anything. Although you are seeing something, the uncertainty remains the same. Right? You get absolutely no clue whatsoever X. Similarly, this yes is, so this R is called the random blinder. So if I use a random blinder, the secrecy can be preserved. No information about that will be leaked. Okay? Let me give you a simple example, minor modification. I have my X, I have R. R could be a positive or negative even number, and I get 40. Now what can you say about X? R is even. X must be even. The last bit is 0. I got one bit of information leaked now. Right? My 40 has leaked one bit of information. That is because my random choice is very poor. Now you got one bit of information out. Right? Therefore, you can see that you are getting some clue, some leak about the secret happening. There's no leak about the secret will happen, whatever is the number of times we play. Okay? Again, let us play. This time I am going to choose another random number. I am not going to use the same random number. I played once. After 5 minutes, let us play again. I have a number in my X. I add another random number and the answer is 70. What can you say about it? Again, I can play any number of times. The random blinder has a property that it leaks nothing, absolutely nothing about the secret. It's a very powerful and important technique. Again, see how randomness plays the role. So, this K is a random blinder. E is selected by verifier, but EX, I not only multiply, I add a K, and this random blinder makes S to look random. 40 could have come from any value. So you have no clue. Same way, S gives no clue even if you play multiple rounds. Provided every round I choose this K randomly. That's what I will do. So the commitment will be done. Every time a random commitment will be done and you play, you are safe. Your secret will not be known. You can play 1,000,000 times. You can play 1,000,000,000 times. It doesn't matter. Nothing will happen to your secret. It is always protected. But you are able to convince every time when you interact to a verifier. Zero knowledge protocol. Okay? So many beautiful properties. All I have told you is in a very high level. What is formalism that is needed? The formalism that is needed is really deep mathematics and probability theory. Okay? So, what do you mean by actually zero knowledge is following this spirit. There is a distribution. What is the distribution? Modeling my uncertainty, modeling your uncertainty. I have a number in X in my mind between 1 and 100. It's an integer. So, it could be 1 or 2 or 3 or 4. Your uncertainty is modeled by a discrete distribution, 1 by 100, 1 by 100, 1 by 100 and so on. So there is a probability distribution. And after seeing this, again there is a probability distribution. if there is a leakage, there will be a difference in distribution. For example, if R is even, earlier my distribution was 1 by 100 or 1 by 100. The moment I know X is even, this is 0, this is 1 by 50. This is 0 and this is 1 by 50. So in this way, you see that the distribution changes. Right? So there is a distribution that is coming into picture here for what is known as a transcript. What is a transcript? Transcript is the triplet K, E and S. First K is used and then E is used, then S is sent. This, how much information it leaks about the secret X. In order to do that, you have certain uncertainty about the secret. Even after seeing, the same uncertainty is maintained. In other words, the distribution after and the distribution before are one and the same. They are identical distribution. This is what you have to show. So this is where statistical similarity, statistical closeness, all of them are used. Okay? Identical nature of statistical distributions, closeness of the distribution. If you are not able to write a protocol in which it is identical, make sure that this is statistically close to the distribution that you have when the secret is known. Right? Statistical zero knowledge. And like that you have various things, and each one of them have their own complexity, computational complexity. Okay? And the area expands to cover various protocols applied in various contexts. Alright? So you have a formal definition for zero knowledge protocol, which is there in terms of the distribution of the transcripts, and formal proof of that will require showing all those kind of things. Very rich mathematics, very sophisticated application of probability theory, all of them are involved. But it is done with respect to a real life protocol. The protocol is dynamic. This is, that's what is making the things very challenging. These are not fixed mathematical entities whose properties are to be proved. This is something that is dynamically generated in a protocol whose probabilistic properties are to be proved. That's a real challenge. Okay? There are a lot of deep mathematics in it. Very challenging and then exciting mathematics in this. And the research area is growing actively in this. Okay? So, with this very brief remarks about zero knowledge protocol, let me conclude the talk. If there are any questions, I would like to take the questions. Any questions? Yeah, question here. Huh? Yes, he will be able to observe, but he can't repeat. The reason is the E that is sent by is different. Let us say you have observed my first interaction. I have sent 10. This fellow has sent 45. Then I have sent a response. For 10 and 45 you know the response. But so when you try to play, you can also send 10. But next time he is going to select another random value. This E is random. Right? So for the new one, you have no way to select the response.
But like, can't he calculate X from that?
How will you calculate? That is the question. How the X can be calculated? This is known. S is known. K is not known. What is sent is G power K. G power K is known. K is not known. From G power K, can you find K? You can't. That is a discrete log problem. That is a one-way function. That is the reason why, although the clue for K has gone, no one can find the K. Of course, if K can be found, this is known. S is known, K is known, E is known, you can find X. Unfortunately, well, fortunately, K cannot be found. It is a random value that cannot be found and determined, and that is acting as a blinder, so your X is safe. Yeah, question here.
So then if there's no limit on the number of times you can play this game,
Yeah.
and if I'm an impersonator and I keep, instead of sending like random g power k, if I keep sending the same thing or like some sort of pattern,
Yeah.
can I not figure out some pattern and figure out?
Exactly. That is the reason why you can, the P star can choose K in a malicious way, but V is generating random E all the time. Right? And first of all, after sending this, the attacker will never be able to succeed. He's going to fail. Because he is going to select some random yes and then he will send, hoping that it is capturing yes. It's not going to do. And then, how many possibilities are there? P is 2 power 256. Remember, 2 power 80 itself is an impossible number. And you have the choice. And you are going to play 20 times. This we have what is known as the number numbness. We don't feel that 2 power 256 as a real big number. Right? Actually, it's never going to happen. The number of choices are trillion times, which you can't even describe in English word, and that many options, and then he is going to fail overwhelmingly. That is the reason why he can play 100 times, 200 times, 1 billion times. Still he will get no clue. Because 1 billion is 2 per 30 or 20. 30. Minuscule compared to this. Therefore, in real world, in real life applications, it's never going to happen. The probability is non-zero, but then it is so close to zero that we take it as zero. Okay? Yeah. Question?
So like we discussed that the two ways where like the initial algorithm, not the zero knowledge proof, can fail where either the V is compromised or in between there is a
Yeah.
So in case both of these happen simultaneously.
Yes.
So will this still tackle the zero knowledge proof?
It won't. Because an honest prover is always going to select a random key. Let V be malicious. Doesn't matter. What are the information V has? V has G power K, E and S. V doesn't have, and V cannot find K. The person who is watching, what does he has? He has also G power K and E and S. What is the knowledge that the rest of the world has? The rest of the world has G power K, S and E. With this knowledge, you can't crack X. Whether it is impersonator, whether it is a malicious one, X is there only with P. X is not there anywhere outside. Of course, X travels in S, but S is using K as a random blinder, and K is impossible for anyone to compute. Given G power K, that is the one-way function which I am using. That is the number theoretic reference problem, hard problem. Discrete log problem is hard. Under that assumption, we are working. Okay? As on today, we do not have any efficient algorithm for discrete log. But if discrete log problem can be solved in polynomial time, this is broken. Remember, the security of this is depending on the assumption that discrete log problem is one-way function. If that is broken, this protocol is broken. Because K can be found. If K can be found, X can be found. You are ruined. And that is what is happening in quantum world. Quantum computers can find K given G power K in polynomial time. So if you are armed with a quantum computer, you can break this. If you have only the computer that I have, you can't.
Okay, we'll take one last question. Please, other questions, please drop off time.
So if we, if K follows some distribution,
yeah,
couldn't we repeatedly send 0 as E, find out the expectation of K, and then repeatedly send E as 1?
The number of interaction you would require will be exponential. That is where the difficulty, because what we are trying to look at is polynomial time breakability. In polynomial time, is it possible for you to break? So in polynomial number of triplets. Okay, assume that I have this triplet fail. Okay, with polynomial number of triplets, how much information you can get?
But could
It
you
will
get-
be negligible.
Could you get arbitrarily high confidence intervals?
No, even that's what. That's where we have the notion of negligible probability. Like polynomial time computation is closed under polynomial time composition, the negligible probability will remain negligible even if you repeat the experiment polynomial number of times. Because negligible probability is a probability like 1 by 2 power n. So you put some f of n, some polynomial p of n in the numerator, still this is negligible. Because what is there in the numerator is polynomial, but what is down there is exponential. So still your probability of success is negligible. Okay? It is going to remain negligible. That is how the argument will be built. Why that we will not be able to get any success? The probability of succeeding is negligibly small. That is, it will be exponentially small. So you play polynomial number of times. When you play polynomial number of times, of course, your probability of winning increases, but to how much it can increase? To this much it can increase. But this is still negligible, that you are still safe. Okay? You do have mathematical guarantees of that kind. That's deep math. Of course, it is math. That's why we give formal proof of correctness, formal validity, and a formal argument on the robustness of the protocol. Is it secure? That question to answer formally requires fairly deep and good amount of math and good amount of explorations in the subject. Okay? And we have Arpita Patra kind of experts here in CSA department. They are doing a lot of work on multi-party computation, reducing the number of round complexity, achieving the high probability guarantees and all those things. They are all working. We have, you might have seen in the first slide, zero knowledge protocol as an area of research by the cryptography group here. Okay, IISc faculty members are very actively doing that. And then of course IIT Madras also, Dr. Shweta, she is an expert in these kind of protocols and then giving technical guarantees for their robustness. Okay, she is of course working in post-quantum cryptography. Even if there is a quantum computer, how do I make sure that my protocol doesn't break? The protocol that I described cannot be broken by regular computer, but not by quantum computers. Post-quantum cryptography is an exciting area, and that is very actively pursued at IIT Madras, one of the leading centers of the nation pursuing post-quantum cryptography. Okay, everything is studied in post-quantum context.
Okay, let's thank the speaker.
Thank you very much. Thanks for your patience, and now you can now go ahead for lunch and other announcements. They are eagerly waiting for.
Okay, so we'll break for